Hey guys, I'm sorry I'm not there with you guys today, but let's go over the first half of 8.2. Right, so last time we started talking about vectors, and one of the things we ended with is how to break a vector into its horizontal and vertical components, right? All right, so we're going to pick up from that. So suppose I have a vector here. Whoops, sorry. Suppose I have a vector here. It starts at point A, goes to point B, initial side to terminal side, right? And I want to express this vector in component form, right? So basically, one way to go from the initial point to the terminal point, right, is along this vector right here from A to B. Another way to do that is go horizontally a little bit, right? Starting at point A, and then go vertically a little bit and reach point B, right? So suppose the distance that you go horizontally is, I don't know, 3 units. And suppose the distance that you go vertically is 4 units. Then the horizontal component of this vector is 3 units long, and the vertical component is 4 units long. So we say this vector AB can be written in component form in these, I call them, triangular brackets. They're just pointy brackets. So if we go over 3 units horizontally and 4 units vertically, then this notation, vector AB equals 3 comma 4, is called the component form of this vector. And basically it provides a recipe on how to recreate that purple vector. So essentially, if you start from a point, go 3 units this way, 4 units that way, you have your ending position, and that is how you can recreate your vector. All right? Now, most of the time, you will be given just coordinates of the initial and the terminal points. So for example, suppose the initial point is at 1 comma 3, and then the terminal point is at 4 comma 7, right? So now the horizontal component, if I'm going to go from 1 to 4, well, that will be x2 minus x1. And the vertical component will be 7 minus 3, y2 minus y1, right? So that's why we say the component form of a vector can be written as this, where the x component is x2 minus x1, and then the y component is y2 minus y1. So take a look here. We want to find the component form of vector AB with initial point A and terminal point B. So we say AB is equal to, okay, so for the x components, always final minus initial. So terminal minus initial. So 1 minus 1, comma, and the y component will be 3 minus negative 3. Okay, obviously you don't have to show me this arithmetic here, right? I know you guys can do this in your head. So the component form of vector AB is 0 comma 6, right? Okay, so let's just plot this and see what exactly we're talking about, right? So here, the initial component, the initial point is 1 comma 3. So here, 1 comma negative 3. So that's right here. That's point A. And then the other one is 1 comma positive 3, point B. So if I were to draw this vector from A to B, it would point that way, right? So is 0 comma 6 an accurate representation of this vector? It definitely is, because if I start from the initial point A, how do I get to the terminal point? Well, I go 0 units horizontally, 6 units vertically, and that's exactly where the terminal point lies. Okay? All right, now, Let's talk about magnitude. Since magnitude of a vector is basically the actual length of the vector, then if you have the horizontal and the vertical components, then basically you just need to use the distance formula, or which is the same as the Pythagorean theorem. It's based on the distance formula, right? So if I knew the x component and the y component, how would I find the length of vector v? I would basically do 3 squared plus, I meant that to be a 4. 3 squared plus 4 squared, right? So I would have to do the x component squared plus the y component squared, and all this has to be in a square root, right? That's the distance formula. So this is how we find magnitude of a vector, right? So it's the square root of the x component, x2 minus x1 squared, plus y2 minus y1 squared. Now, suppose I do have a vector in component form, right? Just like we had up there. So suppose it's 3, 4. If it's already in component form, then it becomes even easier. This becomes little a, and this becomes little b. So then the magnitude of the vector is the square root of a squared plus b squared. All right, so find the magnitude of AB with the same initial points as in example 2. Well, we had put AB in component form, remember? It was 0, 6. Now, to find the magnitude of AB, all you have to do is square root the x component squared plus the y component squared. This is the square root of 36. So the magnitude of vector AB is equal to 6. And looking at our green vector from example 1, does that have a magnitude of 6? It does. Okay. All right, now let's talk about vector operations. You can add, subtract, and multiply a vector by a scalar, and it's the same exact format as what we did for matrices. In fact, let's think about this for a minute. What if I had a 1 by 2 row matrix and the components were 3, 4? Well, now what if I took that and I wrote it like this? Oh my God, what just happened? What just happened? A vector. What? Is it just a row matrix? Oh my God, I would have never ever guessed. So that's the connection, right? A vector is just a simple row matrix. So I can add and subtract vectors just like I would matrices. Okay, so if I wanted to add vector A plus vector B, I just add the first components and then the second components. It's literally the same as in matrices. So why don't we do a couple of examples then? Okay, so find each of the following. So we have vector W, Y, and Z. We want to find 2W plus Y minus 4Z. Okay, 2W means 2 times 2 comma negative 5 plus Y 2 comma 0 minus 4 times negative 1, negative 4. So this is going to be, distribute this, right? That vector becomes 4 comma negative 10 plus 2, 0. Now here, if you distribute the negative, then this is going to be plus negative 4 times negative 1 is 4, 16. So now the sum of this, right? You take all of the first components, the horizontal components. So the 4 plus 2 plus 4, that's 10. And then the y components, negative 10 plus 0 plus 16, 6. So that's what we get as our vector. All right, next. What is a unit vector? A unit vector is basically a vector with a magnitude of 1. And but it will have a specific direction. So suppose you had a vector v. Its unit vector, we'll call it u, will have the same exact direction of v, but it will have a magnitude of 1. So take a look here. This blue vector, this entire blue vector is vector v. Okay? That vector has a length of 2.5 units. The unit vector is vector u. It has a length of exactly 1 unit, but do you see how it lies exactly on top of vector v? It has got identical direction with vector v, but it's just 1 unit long, all right? So it basically can represent the direction of something. If you just want to know where something points, you don't have to carry around a vector that is like 700 units long in your pocket, right? You could just have like a little unit vector and it'll tell you exactly where your vector should be pointing, all right? Now, how do we find a unit vector? Well, it's so simple. You basically take vector v in component form and divide it by its magnitude. So I have a couple of arrows missing here. Vector u is just vector v divided by the magnitude of vector v. Okay, so let's find the vector u with the same direction as this vector v. Oh my gosh, I don't know where these arrows went. It's like there's an arrow thief. Okay, so first what we need is the magnitude of vector v. So the magnitude of vector v is the square root of 4 squared plus negative 2 squared. So this is the square root of 16 plus 4. This is the square root of 20, which is 2 root 5. And we're just going to leave it that way for the time being. Now, I want to find vector u. To do that, I'm basically going to take my vector v and I'm going to divide it by this magnitude 2 root 5. Well, that's the same as, okay, remember when you divide or multiply something by a scalar, you have to divide or multiply each component with it. So that's basically going to be the first over 2 root 5, comma, the second over 2 root 5. So u is going to be, cancel that, 2 over root 5, negative 1 over root 5. Okay. And you know what? This seems really, really abstract for the time being. So I'm actually going to show you what it is that we have done here, right? So look at this. The original vector we had was 4 comma negative 2. And then the unit vector turned out to be, this business. So you know what I'm going to do is I'm actually going to plug this into my calculator and I'm going to see what these, crazy numbers add up to. So basically, when you do that, 2 over root 5 is 0.89. And then, this is negative 1 over root 5 is negative 0.45. Okay, roughly. This is very much rounded here. So what I'm going to do is I'm going to go over to some graph paper here. And what I'm going to do here is first I'm going to graph our initial vector. Remember the initial vector was 4 comma negative 2. Okay, so why don't we draw that? So this says we're going to go 4 in the horizontal direction, 2 in the negative direction because it's negative 2. So if my initial point is at the origin, the final point will be here. The terminal point will be here. So my vector will look like this. Now this is vector v. All right. Okay, what did we say vector u was? We just said vector u turned out to be 0.89 and negative 0.45. So why don't we now draw that? So from here, I'm going to go 0.89 roughly this way here. and then halfway down to 0.45. Oh my God, wouldn't you know it? That lies exactly on top of the original vector. That's how big vector u is. And if I were to measure that, it would be exactly 1 unit long, right? So if you were to do the Pythagorean theorem on this, or the distance formula on that, it would have a length of exactly 1. Okay? You don't believe me? Let's try it because it's really important. So what do we have here? 2 root 5 over negative 1 over root 5. So let's see that. Let's just see what the magnitude of u is. We're going to take in the square root the first one squared plus the second one squared. So this is in the square root 4 over 5 plus 1 over 5. Oh my God, it's in the square root. I got 5 over 5. Guys, this is the square root of 1, which is 1. So the magnitude of that red vector is in fact 1. And if this is not the most satisfying, coolest thing you will ever see in your lives, then I don't know what is. All right? So that's what a unit vector is. Trust in the math, even though you look at some numbers and it seems abstract, but you know what? Trust in the math. All right, so that's how you find a unit vector. Now, this unit vector, we said, points in the same direction as v, right? However, we can have unit vectors pointing in any old direction. And we're now beginning to figure out that vectors that are purely horizontal or purely vertical are in fact special beings. And the unit vectors that are purely horizontal and purely vertical are also special beings. In fact, they are so special, they have their own name, and that is vector I and vector j, right? So I is a unit vector that is only in the horizontal direction. It lies along the x-axis. Its components are 1, 0. J is in the vertical direction, 0, 1. Now, in shorthand, I and J, these are actually given special symbols. In fact, they're written as I with a little hat on top, and it's literally called I hat. And I hat is 1, 0, and J hat is 0, 1. I hat and J hat. In fact, a couple of years ago, I was this close to writing, a little children's book, The Adventures of I hat and J hat, but alas, it never materialized. So I hat and J hat, pretty big deals. These are the unit vectors in the horizontal and vertical direction. Oh, how come my formatting went awry here? Okay, so basically, I can have a combination of I hats and J hats, and together they can create any old vector that I would like. So here, for example, look at this. I've got 1, 2, 3 I hats and 1, 2, 3, 4 J hats, and together they work together. They collaborate to create that vector. Okay, so this vector V can be written as 3, 4 in component form, or it could also be written as 3 I hat plus 4 J hat. And that is a representation as a linear combination of I and J. Okay, linear combination of I and J. All right, so I'm really sorry about the formatting here. I hope it's just my copy and not yours as well. But basically, it says here that DE is a vector. Oops. DE is a vector with initial point D -3, -3, and terminal point E 2, 6. And we can see here we want DE as a linear combination of the vectors I and J. Okay, what I like to do first is put this in component form. So how do we put this in component form? All right, so DE is going to be, all right, the x components, 2 minus negative 3, and then 6 minus negative 3 for the y components. So DE in component form is 5, 9. And then after that, if I wanted to write this as a linear combination of I and j, then all I would say is DE is equal to 5i plus 9j. Okay? All right. And of course, like, if it was, let's say, negative 3 comma 2, then it would be negative 3i plus 2j or minus 2j or whatever. Okay? All right. Actually, I'm just going to stop here because I hat and J hat, deserve a little pause for themselves. We will continue the rest tomorrow. Now, the homework that you have is actually already split. So you're going to do homework 32. That takes you directly to this point right here. All right? Okay, everybody, have a wonderful day. I'll see you next class.